Here we will discuss the first nucleophilic addition reaction to aldehydes and ketones. This first reaction will be the addition of hydrogen cyanide, HCN. So let's write out the general reaction scheme. So we start with an aldehyde or a ketone. We'll use just two R's to represent what's bonded to the carbon. We of course have our carbonyl. And then we add hydrogen cyanide. I'm going to emphasize the hydrogen in blue here, and then the rest of the molecule in pink. So we have hydrogen bonded to a carbon, triple bonded to a nitrogen. That's hydrogen cyanide. This is a reversible reaction, occurs in solution with a pH between 9 and 10. Our product, we have the R groups still bonded to the carbon. We've added a nucleophile. The carbon to oxygen pi bond is now just a single bond. So we have oxygen, it's bonded to the hydrogen from hydrogen cyanide. And then we also have that carbon bonded to the nitrile group, carbon triple bonded to nitrogen. So here we have the nitrile functional group. And of course the alcohol on top of the carbon, the way we've drawn it here. So before we get into the mechanism, let's think about why it's important that this reaction happens at a relatively high pH, at a pH between 9 and 10. Well, it's important to think about the pKa of hydrogen cyanide. So the pKa of hydrogen cyanide is 9.4. So if the pH of the solution is right around the pKa of hydrogen cyanide, that means that the acid, hydrogen cyanide, and its conjugate base are present in solution in equilibrium with each other. So pH of 9 to 10 is slightly basic for water. So we can write out this equilibrium equation. We have hydrogen cyanide, and we know this is an acid, has a pKa of 9.4, so it will exist in equilibrium in its associated and dissociated forms. We can write out the equilibrium equation by showing the hydroxide anion. We have a high pH, so slightly basic solution, so we have hydroxide anions present in solution. So we have these two present, and then they are in equilibrium with the conjugate base of hydrogen cyanide, which is just CN. We have a lone pair on carbon with a negative charge, lone pair on nitrogen on both molecules. We can draw the bonding here. This is carbon triple bonded to nitrogen. And then we also have H2O. So all these are in equilibrium with each other. We could draw the reaction arrow for this proton transfer. Electrons from the hydroxide oxygen form a bond to the hydrogen cyanide hydrogen, and then that bond breaks and puts electrons on that carbon, and that's why we have a negatively charged carbon. So having the pH near the pKa of hydrogen cyanide allows there to be in solution both hydrogen cyanide and deprotonated hydrogen cyanide, so CN minus. Now this is the cyanide ion. In the cyanide ion, we have a negatively charged carbon with a lone pair of electrons. This is a great nucleophile. So now we can do nucleophilic addition. So that's the whole reason we have the pH at between 9 and 10, so we can generate this nucleophile in solution. Now that nucleophile is what will react with the aldehyde or ketone. Having hydrogen cyanide only in solution, not in its deprotonated form, would not then be a good nucleophile and wouldn't be adding to the aldehyde or ketone. So now let's look at the mechanism to really understand where electrons are transferring. We'll use what we know about these different molecules to reason through the mechanism. We'll use a real molecule here. This is acetone. This is what is used in a lot of our chemistry labs as a solvent or as a way to clean glassware. It's also nail polish remover. It's very widely used. So this is acetone, a ketone. Now we have generated our nucleophile. So let's draw our nucleophile here, the cyanide ion. We'll label this nucleophile. And then remember, when we have a ketone or aldehyde, that carbonyl carbon is electrophilic. So we have a nucleophile and an electrophile present in solution. They're going to bond together. So I'll use this blue color to show the actual curved arrows for this. The nucleophile, the carbon with non-bonding electrons, creates a bond to the carbonyl carbon, which is electrophilic. It's lacking electrons. And then the pi bond between carbon and oxygen breaks. Before we draw the products, we'll write a note here. This reaction is driven by oxygen's ability to accept electrons. So because oxygen is electronegative, it can accept those pi electrons. That causes that carbon in the carbonyl to be electrophilic, lacking electrons, and the carbon in the nucleophile, since it is nucleophilic, has electrons to share, will create a bond to that carbonyl carbon. So this reaction is driven by oxygen's ability to accept electrons. So it's electronegativity property. I use E-neg with a capital N to shorten electronegativity. So because of oxygen's electronegativity property, that's what really drives this reaction. So this step is reversible. It's favored in the reverse direction, but it is in equilibrium. And one of the products here is a charged tetrahedral intermediate now. So focusing on what the product is here. We'll start with that carbonyl compound, that ketone. We've broken the carbon to oxygen pi bond, but the carbon to oxygen single bond is still there. Carbon is still bonded to the two methyl groups. And then we have a new bond to the nitrile group. Now this is a tetrahedral intermediate. We started with a trigonal planar ketone or aldehyde. Now we have a tetrahedral intermediate, and we'll see this in a lot of reactions generating this tetrahedral intermediate. Now to get to our final product, all we're missing in this molecule is the hydrogen that needs to be bonded to the oxygen. In solution, we have a mixture of hydrogen cyanide and the cyanide ion. In a lot of reactions moving forward, we will have some sort of equilibrium equation of what's present in solution, and we will use different molecules present in this equilibrium equation to carry the reaction forward. So in this step where we have the tetrahedral intermediate, now we need a hydrogen bonded to oxygen. Since both hydrogen cyanide and cyanide ion are present in solution, we can remove a proton from hydrogen cyanide. And that will be how we reach the alcohol functional group in the final step. So now oxygen has a new bond to a hydrogen. We have cyanide ion as a byproduct, and that will then go and add to another aldehyde or ketone molecule. So here's our two-step mechanism for the specific nucleophilic addition reaction. We form this tetrahedral intermediate, and so that means that in our product, we might have a new stereocenter. Now it depends on what groups are bonded to the carbonyl carbon to begin with, but let's focus on geometry. We'll use a general aldehyde or ketone to start off with and think about how stereochemistry is preserved in this reaction or not preserved. So we start with an aldehyde or ketone, and let's draw the orientation where we have one of the single bonds going away from us and one coming towards us. And we'll just use generic groups R and R prime. So we'll say these are two different groups. Doesn't really matter what they are. They're just going to be two different ones. So one is R, one is R prime. We have that pi bond between carbon and oxygen. And we have a 120-degree bond angle between all three bonds here. So that's characteristic of sp2 hybridized atoms. The carbon here is sp2 hybridized. We can also emphasize the planar nature of this. So if we draw, just kind of trying to show that all of these molecules would be in the same plane, or all of these atoms would be in the same plane. So this is meant to show a 2D plane right here. Let's see that. Let me recolor that. Okay, so everything that's part of this molecule is in one plane. So we have an sp2 planar molecule. An sp2 carbonyl carbon, and we're focusing on that carbonyl carbon because that's where that new bond is formed, is to that carbonyl carbon. So that's sp2, we have 120-degree bond angles. And the p orbitals are perpendicular to the plane that the rest of the molecule is in. So if the molecule is in a flat plane coming towards you and away from you, the p orbitals are perpendicular to that, going up and down. So since this molecule is planar, the p orbitals are going up and down, depending on how you draw it. They're perpendicular to the plane. The way we've drawn the orientation here, we can say that now the nucleophile can add below the molecule, so under the plane, or it can add above the molecule, so on top of the plane. These two different bonding orientations will result in different stereochemistry in the product. So the nucleophile can bond above or below the plane. So now we can we'll draw two possible intermediates, one where the nucleophile adds above the plane and one where the nucleophile adds below. So let's do a nucleophile adding above. If the nucleophile, so we have the plane that the molecule is in, I'll use this hand, plane that the molecule is in, the nucleophile comes and adds above the plane that the molecule is in, it'll kind of shift those bonds to the oxygen and R groups down. So we can draw that intermediate as having the nucleophile bonded above the rest of the molecules, above the plane that the molecule was previously in. The R groups are now pointed a little bit away from the nucleophile on the wedge and dash, and then the oxygen, which in this step becomes negatively charged, can be shown on that straight line bond. So that's one intermediate where the nucleophile adds above the plane. If the nucleophile adds below, we have the new bond to the nucleophile below the carbon in this case, and then all the bonds as far as straight line, wedge, and dash can stay the same. But now they're pointed in a different orientation relative to the other groups. So we have R and R prime. So these are both possible intermediates, both will form. These have different stereochemistry, so we get both stereocenters as products. So let's write some notes here. We started with a planar molecule, now we have tetrahedral molecules. That carbonyl carbon is now sp3. Our bond angles in an sp3 geometry or hybridization is 109.5 degree. And this is where we can form a possible stereocenter This is if all four groups are different. If all four groups are different, we have a stereocenter. And so in this reaction, both stereocenters form, so both R and S. So if we just finish out this reaction and draw the products, we have one stereocenter, one stereochemistry. Nucleophile adds above the plane of the molecule. The oxygen is now bonded to a hydrogen, so we have a neutral oxygen. And then our two R groups, one R and one R prime, bonded to carbon. And then the other product is the enantiomer, where now the nucleophile is added below. and we have all the other groups shown above. So we've shown enantiomers differently in the past, where what we've done is switched what's on the wedge and the dash. You could also draw enantiomers this way. This is the mirror image. So if you take this molecule, and I just moved it down here just to demonstrate, we put a mirror in between these two. These are the reflection of each other. And that's the definition of an enantiomer, is that they are the mirror image, non-superimposable mirror image. And that's what we have here. So a couple things to remember, that we start with a planar molecule. When the nucleophile adds, we form a tetrahedral molecule where both stereocenters would form. If we do have 4 different groups, you would have both stereocenters in the product.